we are going to talk about motion in a plane. So, motion in a plane. In this chapter, we are going to talk about two important issues. The first one being the projectile motion. It's a very important concept every one of us need to understand. The second one is the circular motion. So these are the two topics that we are going to study today. Well, before we get into the details of projectile motion and circular motion, let's have some preliminaries, some basic understanding behind motion in a plane. Whenever we say motion in a plane, we need two coordinates. One may be x, the second may be y. Or you can go on with z and y and z, or any two such Cartesian coordinates. This being the origin. The origin is naturally the position where an observer is standing. This is also the position of the observer. Alright, suppose you consider an example like a lizard crawling on the wall, and the lizard may choose to go in any path. Instead of taking a lizard having a significant size, we may replace the lizard by a single point. We call this point as particle. The particle is at point P at a given instant of time. So with respect to the observer, or from the origin, if you draw a vector and we call this vector r, that vector r gives the position vector. Notice the fact that the point P is characterized by two coordinates, namely x and y. Meaning x is the distance to point P along the x-axis and y is the distance to point P along the y-axis. And naturally, if you could consider a unit vector I cap in the x direction, and if you could consider a unit vector j cap in the y direction, we may write r vector as x I cap plus y j cap. This is called the position vector, or position of the particle. The position of the particle at a particular time instant is given by r vector equals x I cap plus y j cap. Now what if this particle changes its position, meaning if this particle were to change, if it were to move along this path. So let's redraw that diagram again. So initially the particle was at point P and later on it is found at point Q. Therefore, point P is indicated with the help of the initial position vector r1, and Q is indicated with the help of the final position vector r2. In this process, you see that the particle has changed its position from P to Q, and if you were to draw a vector from P to Q directly, we get a vector called the position difference or displacement. Displacement vector delta r, or equivalently you could write it S vector as well. You may see that P is having the coordinates x1, y1, and Q is having the coordinates x2, y2. Meanwhile, this is x and this is y. We have already seen in the previous vectors and scalars chapter that if you have a vector A like this and vector B like this and vector C like this, you could always write vector C, which is the closing side of this triangle OAB, as vector A plus vector B. Conversely speaking, vector B, this vector for example, can be rewritten as vector C minus vector E, meaning from this vector, if you subtract this particular vector, you get the difference vector, you call it B if you will. So therefore, this vector R2 is like C here, R1 is like vector A here, and delta R is like vector B there. So we can easily write delta R, the displacement vector, as R2 vector minus R1 vector. This is called the displacement vector in 2 dimensions. Meanwhile, you may also write vector R1, that is the initial position vector, initial position vector of the particle as R1 equals x1 I cap plus y1 j cap. Similarly, final position vector or final position of the particle, you may write R2 vector equals x2 I cap plus y2 j cap. If you take the difference between the two, you get therefore the displacement delta R vector is going to be R2 minus R1, which we have already written here, is x2 I cap plus y2 j cap minus x1 I cap plus y1 j cap. If you remove these brackets and then club the coefficients of I cap together and club the coefficients of j cap together, you will get x2 minus x1 I cap plus y2 minus y1 j cap. But wait a minute, what is x2 minus x1? For example, this much is x2, this much is x1, so the remainder, this much is delta x. Similarly, this much is y2 and this much is y1. So the difference between the two, which is basically this length, which is y2 minus y1. So we could call this delta y. Likewise, delta x is x2 minus x1. So delta r, if you were to rewrite that vector somewhere here, somewhat like this, delta r is going to have two components. One along the x axis, we call it delta x, which is x2 minus x1, and delta y is going to have the components y component is going to be delta y equals y2 minus y1. So delta r vector can now be written as x2 minus x1 I cap plus y2 minus y1 j cap. Since we have already chosen a new notation for x2 minus x1 as delta x and y2 minus y1 as delta y, we may finally write the displacement in general as delta r equals delta x I cap plus delta y j cap. As and when you have a problem in understanding what is delta x and delta y, you may always write where delta x equals x2 minus x1 and delta y equals y2 minus y1. Well, now at this point P, at what time instant did the particle pass through this point? Call it time instant t1. At what instant of time did it pass through point Q? Let us call that time instant t2. So how much time did elapse between the two if I call the delta t, which is t2 minus t1. And now if I take the ratio of delta r by delta t or divide this displacement by delta t, what do I get? So I get delta r by delta t, right hand side delta x by delta t times I cap plus delta y by delta t j cap. So obviously the term on the left hand side is displacement by time taken. We know displacement divided by time taken is nothing but the average velocity. and let's be specific about the notation. We will write this V average arrow mark. So therefore, the left hand side, therefore, this left hand side is going to become V average, and this right hand side first term, that is V average X component into I cap. This one V average Y component into J cap, where V average X is delta X by delta T, displacement in the X direction by time taken. Similarly, V average Y component of the average velocity is displacement in the Y direction by time taken. One more point that I must tell you about the direction of the average velocity. You know, average velocity by definition is given by displacement by time taken, or you may even write this 1 by delta T, which is basically a scalar, times delta R. Notice delta R is a vector, so is the average velocity. 1 by delta T is always a positive quantity because delta T, the time interval, is always positive. 1 by a positive quantity is always a positive quantity, and therefore delta R, whatever the direction of the vector delta R, average velocity vector must also be in the same direction. For example, in this simple elementary example, we have chosen delta R direction to be this way. So naturally, the direction of the average velocity must also be in that direction. Since the average velocity is in this direction, this is the average velocity direction. It is going to have two components. We have already seen V average X in the X direction, V average Y in the Y direction. Thereby, the two make an angle theta. Sorry, the average velocity makes an angle theta with the horizontal. We can easily find the angle made by it. That angle in turn gives the direction of the average velocity. You can see from this right angle triangle that tan theta is going to be opposite side V average Y by adjacent side, which is V average X. Or you may even write theta equals tan inverse of V average Y by V average X. What about the magnitude? So this expression, of course, gives the average velocity both in magnitude and direction. But here we have synthesized that in terms of direction only. How to find the magnitude? How much is the strength of the average velocity? How do we know that? The magnitude of the average velocity, magnitude of average velocity, V average or V average modulus, is square root of average velocity X component square times average velocity Y component square. Very, very simple. So this is the magnitude and this gives the direction. Fine. This average velocity basically tells us, average velocity tells us on an average how fast the particle moved from point P to point Q. But it does not exactly tell us how fast it was moving right at point P itself, or say it was moving, how fast it was moving at point Q itself, or in which direction. To be able to find that, we require what is called as the instantaneous velocity. How do we get the instantaneous velocity? Instantaneous velocity, for example, delta t is the time interval. If we make this t2, become so come so closer to t2, then t2 and t1 become almost a single instant. When t2 becomes almost equal to t1, delta t tends to become 0, meaning when I subject this delta r by delta t to limit delta t tending to 0, as per calculus we have seen delta y by delta x limit delta x tends to 0. This is going to become a calculus parameter called dy by dx, differentiation of y with respect to x. Suppose this were a vector function, for example, some vector say L vector, then accordingly here also you are going to have dl by dx or dl by dt, any parameter for that matter. So we want therefore a quantity which gives us the velocity of the particle moving in the plane at a given time instant, and that quantity we call it instantaneous velocity. Instantaneous velocity, or from now on simply velocity, and from now on its notation is going to be v vector. So how do we find the instantaneous velocity? Suppose there is a particle moving in a plane. So we will copy the same path as we did for the previous analysis. So suppose the particle was initially at point P and later it moved to point Q. This would be the displacement. The time instant at which it passed through point P was t1, the time instant at which it passed through Q was t2. If you make t2 progressively smaller or lesser and lesser and lesser and lesser, so that point Q tends to become closer and closer and closer and closer to P. At one point when t2 tends to become t1, then delta t tends to become 0, then t1 and t2 become almost inseparably the single point. Moreover, the direction of the average velocity is always given along the direction of the displacement. If this is the displacement delta r, this is the average velocity direction. But in other words, the average velocity is always along the chord drawn to the graph, chord drawn to the path. What if Q tends to become P itself? Then the chord becomes a tangent. Well, that point we will concentrate or focus on a bit later. But now, I wish to find the instantaneous velocity. Instantaneous velocity V is limit delta t tends to 0, delta r by delta t, and this ratio we call it dr by dt. In other words, velocity equals rate of change of position with respect to time t. Rate of change of r vector is nothing but position. So rate of change of position with respect to time t is called the velocity. And how do you get the direction of the velocity at a given point? For example, at this point, maybe you can call it m. At that point, what is the direction of the velocity? Very, very easy to find the direction of the velocity. All you have to do is to draw a tangent at that point. And if the particle is moving from, say, this initial point to this final point, then the direction of motion is along that curve, that arrow, and therefore the average velocity, instantaneous velocity must be drawn along the tangent that way. Notice the instantaneous velocity V must be in this direction. Instantaneous velocity again is going to have two components, one along the x-axis, another along the y-axis. The x-axis component is given by Vx, y-axis component is given by Vy. So let us see what this Vx and Vy are equal to. Meanwhile, we already know vector r is going to be x I cap plus y j k. Differentiate this both the sides with respect to time. Dr by dt equals dx by dt into I cap plus dy by dt into j cap. You can notice that I cap and j cap are constant, so therefore they can't be differentiated. So they have been kept outside. Only x and y are changing. So therefore, rate of change of r vector with respect to time t is rate of change of x with respect to time t and rate of change of y with respect to time t into j cap. So comparing this, look, dr by dt by definition is v. Therefore, the left hand side we have v vector. Obviously, this is the x component of the velocity into I cap. This is the y component of the velocity into j cap. So the comparison of the two equations or expressions uses Vx dx by dt and Vy dy by dt. Now often we are interested in finding the direction of the velocity with respect to a specific direction, maybe x-axis. How do we find it? From this right angle triangle it becomes very clear that tan theta is opposite side Vy divided by adjacent side Vx, meaning, so from that right angle triangle we find tan theta equals Vy by Vx. Meanwhile Vy is dy by dt, we have already seen here, divided by Vx, which is dx by dt, we have seen over there, dx by dt, and dt cancel out. So theta can be either written as tan inverse of Vy by Vx or equivalently tan inverse of dy by dx. So the second expression is very, very interesting because, for example, if you are required to know what is the velocity direction at this point, say n, all you have to do is to know how y changes with x. In other words, the y as a function of x. Then differentiate that dy by dx, find dy by dx of that at that point and find the tan inverse of that value. The angle indicates the direction of the velocity. So this is one way. Another way is to know what are the x and y components of the velocity at that point, Vy and Vx. Take the tan inverse or arctan of that, you get the direction of the velocity over there. So this is how you will find the displacement, the average velocity and the instantaneous velocity of the particle. So this is a complete analysis of the three important concepts or three important parameters or three important quantities. So in order to understand it better, let's apply all these concepts to a certain problem.